The actinide ʻæktᵻnaɪd or actinoid ʻæktᵻnɔɪd series encompasses the 15 metallic chemical elements with atomic numbers from 89 to 103, actinium through lawrencium. The actinide series derives its name from the first element in the series, actinium. The informal chemical symbol and is used in general discussions of actinide chemistry to refer to any actinide. All but one of the actinides are F-block elements, corresponding to the filling of the 5F electron shell. Lawrencium, a D-block element, is also generally considered an actinide, in comparison with the lanthanides, also mostly F-block elements. The actinides show much more variable valence. They all have very large atomic and ionic radii and exhibit an unusually large range of physical properties, while actinium and the late actinides behave similarly to the lanthanides. The elements thorium through neptunium are much more similar to transition metals in the chemistry. All actinides are radioactive and release energy upon radioactive decay. Naturally occurring uranium and thorium, and synthetically produced plutonium are the most abundant actinides on Earth. These are used in nuclear reactors and nuclear weapons. Uranium and thorium also have diverse current or historical uses, and americium is used in the ionization chambers of most modern smoke detectors. Of the actinides, primordial thorium and uranium occur naturally in substantial quantities, and small amounts of persisting natural plutonium have also been identified. The radioactive decay of uranium produces transient amounts of actinium and protactinium, and atoms of neptunium and plutonium are occasionally produced from transmutation reactions in uranium ores. The other actinides are purely synthetic elements. Nuclear weapons tests have released at least 6 actinides heavier than plutonium into the environment. Analysis of debris from a 1952 hydrogen bomb explosion showed the presence of americium, curium, berkelium, californium, einsteinium and fermium in presentations of the periodic table. The lanthanides and the actinides are customarily shown as 2 additional rows below the main body of the table, with placeholders or else a selected single element of each series shown in a single cell of the main table, between barium and hafnium, and radium and rutherfordium, respectively. This convention is entirely a matter of aesthetics and formatting practicality. A rarely used wide-formatted periodic table inserts the lanthanide and actinide series in their proper places, as parts of the table's 6th and 7th rows. Discovery, isolation and synthesis. Like the lanthanides, the actinides form a family of elements with similar properties. Within the actinides, there are 2 overlapping groups: transuranium elements, which follow uranium in the periodic table, and transplutonium elements, which follow plutonium. Compared to the lanthanides, which are found in nature in appreciable quantities, most actinides are rare. The most abundant, or easy to synthesize actinides are uranium and thorium, followed by plutonium, americium, actinium, protactinium and neptunium. The existence of transuranium elements was suggested by Enrico Fermi based on his experiments in 1934. However, even though 4 actinides were known by that time, it was not yet understood that they formed a family similar to lanthanides. The prevailing view that dominated early research into transuranics was that they were regular elements in the 7th period, with thorium, protactinium and uranium corresponding to 6th period hafnium, tantalum and tungsten, respectively. Synthesis of transuranics gradually undermined this point of view. Studies of known actinides and discoveries of further transuranic elements provided more data in support of this point of view. But the phrase actinide hypothesis remained in active use by scientists through the late 1950s. At present, there are 2 major methods of producing isotopes of transplutonium elements: irradiation of the lighter elements with either neutrons or accelerated charged particles. The first method is most important for applications as only neutron irradiation using nuclear reactors allows the production of sizable amounts of synthetic actinides. However, it is limited to relatively light elements. The advantage of the second method is that elements heavier than plutonium, as well as neutron-deficient isotopes, can be obtained, which are not formed during neutron irradiation. In 1962 to 1966, there were attempts in the United States to produce transplutonium isotopes using a series of 6 underground nuclear explosions. Small samples of rock were extracted from the blast area immediately after the test to study the explosion products, but no isotopes with mass number greater than 257 could be detected, despite predictions that such isotopes would have relatively long half-lives of alpha decay. This inobservation was attributed to spontaneous fission owing to the large speed of the products and to other decay channels, such as neutron emission and nuclear fission. From actinium to uranium, uranium and thorium were the first actinides discovered. Uranium was identified in 1789 by the German chemist Martin Heinrich Klaproth in pitchblende ore. He named it after the planet Uranus, which had been discovered only 8 years earlier. Klaproth was able to precipitate a yellow compound by dissolving pitchblende in nitric acid and neutralizing the solution with sodium hydroxide. He then reduced the obtained yellow powder with charcoal, and extracted a black substance that he mistook for metal. Only 60 years later, the French scientist Eugene Melchior-Pélaga identified it with uranium oxide. He also isolated the first sample of uranium metal by heating uranium tetrachloride with potassium. The atomic mass of uranium was then calculated as 120, but Dmitry Mendeleev in 1872 corrected it to 240 using his periodicity laws. This value was confirmed experimentally in 1882 by K. Zimmermann. Thorium oxide was discovered by Friedrich Wöhler in the mineral, which was found in Norway. Jöns Jacob Berzelius characterized this material in more detail in 1828. By reduction of thorium tetrachloride with potassium, he isolated the metal and named it thorium after the Norse god of thunder and lightning Thor. The same isolation method was later used by Pélaga for uranium. Actinium was discovered in 1899 by André Louis Debian, an assistant of Marie Curie. In the pitchblende waste left after removal of radium and polonium, he described the substance as similar to titanium and as similar to thorium. The discovery of actinium by Debian was however questioned in 1971 and 2000, arguing that Debian's publications in 1904 contradicted his earlier work of 1899 to 1900. The name actinium comes from the Greek actis, actinos, meaning beam or ray. This metal was discovered not by its own radiation but by the radiation of the daughter products. Owing to the close similarity of actinium and lanthanum and low abundance, pure actinium could only be produced in 1950. The term actinide was probably introduced by Victor Goldschmidt in 1937. Protactinium was possibly isolated in 1900 by William Crookes. It was first identified in 1913, when Casimir Huygens and Oswald Helmut Göring encountered the short-lived isotope 234 MPa during their studies of the 238U decay. They named the new element brevium. The name was changed to protoactinium in 1918 when two groups of scientists, led by the Austrian Lise Meitner and Otto Hahn of Germany and Frederick Soddy and John Cranstoun of Great Britain, independently discovered 231 pascals. The name was shortened to protactinium in 1949. This element was little characterized until 1960, when A.G. Maddock and his co-workers in the UK produced 130 grams of protactinium from 60 tons of waste left after extraction of uranium from its source. Neptunium and above neptunium was discovered by Edwin Macmillan and Philip H. Abelson in 1940 in Berkeley, California. They produced the 239 Nepes isotope by bombarding uranium with slow neutrons. It was the first transuranium element produced synthetically. Transuranium elements do not occur in sizable quantities in nature and are commonly synthesized via nuclear reactions conducted with nuclear reactors. For example, under irradiation with reactor neutrons, uranium-238 partially converts to plutonium-239. In this way, Enrico Fermi with collaborators, using the first nuclear reactor Chicago Pile 1, obtained significant amounts of plutonium-239, which were then used in nuclear weapons. Actinides with the highest mass numbers are synthesized by bombarding uranium, plutonium, curium and californium with ions of nitrogen, oxygen, carbon, neon or boron in a particle accelerator. So, nobelium was produced by bombarding uranium-238 with neon-22 as the first isotopes of transplutonium elements, Americium-241 and Curium-242, were synthesized in 1944 by Glenn T. Seaborg, Ralph A. James and Albert G. Also, Curium-242 was obtained by bombarding plutonium-239 with 32 MeV alpha particles. The Americium-241 and Curium-242 isotopes also were produced by irradiating plutonium in a nuclear reactor. The latter element was named after Marie Curie and her husband Pierre, who are noted for discovering radium and for their work in radioactivity. Bombarding Curium-242 with alpha particles resulted in an isotope of californium-245 Cf, and a similar procedure yielded in 1949 berkelium-243 from Americium-241. The new elements were named after Berkeley, California, by analogy with its lanthanide homologue terbium, which was named after the village of Ytterby in Sweden. In 1945, B. Cunningham obtained the first bulk chemical compound of a transplutonium element, namely americium hydroxide. Over the next 3 to 4 years, milligram quantities of americium and microgram amounts of curium were accumulated that allowed production of isotopes of berkelium and californium. Sizable amounts of these elements were produced only in 1958, and the first californium compound was obtained only in 1960 by B. Cunningham and J. C. Wallman. Einsteinium and fermium were identified in 1952–1953 in the fallout from the IUPAC nuclear test, the first successful test of a hydrogen bomb. Instantaneous exposure of uranium-238 to a large neutron flux resulting from the explosion produced heavy isotopes of uranium, including uranium-253 and uranium-255, and their beta decay yielded einsteinium-253 and fermium-255. The discovery of the new elements and the new data on neutron capture were initially kept secret on the orders of the U.S. military until 1955 due to Cold War tensions. Nevertheless, the Berkeley team were able to prepare einsteinium and fermium by civilian means, through the neutron bombardment of plutonium-239, and published this work in 1954 with the disclaimer that it was not the first studies that had been carried out on the elements. The IUPAC studies were declassified and published in 1955. The first significant amounts of einsteinium were produced in 1961 by Cunningham and colleagues, but this has not been done for fermium yet. The first isotope of mendelevium, 256 Md, was synthesized by Albert G. Also, Glenn T. Seaborg, Gregory R. Chopin, Bernard G. Harvey and Stanley G. Thompson when they bombarded an 253s target with alpha particles in the 60-inch cyclotron of Berkeley Radiation Laboratory. This was the first isotope of any element to be synthesized one atom at a time. There were several attempts to obtain isotopes of nobelium by Swedish and American groups, but the first reliable result was the synthesis of 256 No by the Russian group in 1965, as acknowledged by the IUPAC in 1992. In their experiments, Flyorov et al. Bombarded uranium-238 with neon-22. In 1961, Ghiorso et al. Obtained the first isotope of lawrencium by irradiating californium with boron-10 and boron-11 ions. The mass number of this isotope was not clearly established at the time. In 1965, 256 Lr was synthesized by Flyorov et al. From 243 Am18O. Thus IUPAC recognized the nuclear physics teams at Dubna and Berkeley as the co-discoverers of lawrencium isotopes. 31 isotopes of actinium and 8 excited isomeric states of some of its nuclides were identified by 2010. 3 isotopes, 225 Ac, 227 Ac and 228 Ac, were found in nature and the others were produced in the laboratory. Only the 3 natural isotopes are used in applications. Actinium-225 is a member of radioactive neptunium series. It was first discovered in 1947 as a fission product of uranium-233. It is an alpha emitter with a half-life of 10 days. Actinium-225 is less available than actinium-228, but is more promising in radiotracer applications. Actinium-227 occurs in all uranium ores, but in small quantities. 1 gram of uranium contains only 2 times 10⁻10 gram of 227 Ac. Actinium-228 is a member of radioactive thorium series formed by the decay of 228 Ra. It is a beta- emitter with a half-life of 6.15 hours. In 1 ton of thorium there is 5 times 10⁻8 gram of 228 Ac. It was discovered by Otto Hahn in 1906. 29 isotopes of protactinium are known with mass numbers chapters 212 to 240 as well as 3 excited isomeric states. Only 231 pascals and 234 pascals have been found in nature. All the isotopes have short lifetime, except for protactinium-231. The most important isotopes are 231 pascals and 233 pascals, which is an intermediate product in obtaining uranium-233 and is the most affordable among artificial isotopes of protactinium. 233 pascals has convenient half-life and energy of gamma radiation, and thus was used in most studies of protactinium chemistry. Protactinium-233 is a beta emitter with a half-life of 26.97 days. Uranium has the highest number of both natural and synthetic isotopes. They have mass numbers of 217 to 242, and 3 of them, 234U, 235U and 238U, are present in appreciable quantities in nature. Among others, the most important is 233U, which is a final product of transformations of 232Th irradiated by slow neutrons. 233U has a very high fission efficiency by low-energy neutrons, compared e.g. with 235U. Most uranium chemistry studies were carried out on uranium-238 owing to its long half-life of 4.4 times 109 years. There are 19 isotopes of neptunium with mass numbers from 225 to 244. They are all highly radioactive. The most popular among scientists are long-lived 237 nepers and short-lived 239 nepers, 238 nepers. 16 isotopes of americium are known with mass numbers from 232 to 248. The most important are 241 Am and 243 Am, which are alpha emitters and also emit soft but intense gamma rays. Both of them can be obtained in an isotopically pure form. Chemical properties of americium were first studied with 241 Am, but later shifted to 243 Am, which is almost 20 times less radioactive. The disadvantage of 243 Am is production of the short-lived daughter isotope 239 nepers, which has to be considered in the data analysis. Among 19 isotopes of curium, the most accessible are 242 cm and 244 cm. They are alpha emitters, but with much shorter lifetime than the americium isotopes. These isotopes emit almost no gamma radiation, but undergo spontaneous fission with the associated emission of neutrons. More long-lived isotopes of curium are formed as a mixture during neutron irradiation of plutonium or americium. Upon short irradiation, this mixture is dominated by curium-246, and then curium-248 begins to accumulate. Both of these isotopes, especially 248 cm, have a longer half-life and are much more convenient for carrying out chemical research than 242 cm and 244 cm. But they also have a rather high rate of spontaneous fission. 247 cm has the longest lifetime among isotopes of curium, but is not formed in large quantities because of the strong fission induced by thermal neutrons. 14 isotopes of berkelium were identified with mass numbers chapters 238 to 252. Only 249 Bk is available in large quantities. It has a relatively short half-life of 330 days and emits mostly soft beta particles, which are inconvenient for detection. Its alpha radiation is rather weak, but is sometimes used to detect this isotope. 247 Bk is an alpha emitter with a long half-life of 1,380 years, but it is hard to obtain in appreciable quantities. It is not formed upon neutron irradiation of plutonium because of the beta stability of isotopes of curium. Isotopes with mass number below 248. Isotopes of californium with mass numbers chapters 237 to 256 are formed in nuclear reactors. Californium-253 is a beta emitter and the rest are alpha emitters. The isotopes with even mass numbers have a high rate of spontaneous fission, especially 254 Cf, of which 99.7% decays by spontaneous fission. Californium-249 has a relatively long half-life, weak spontaneous fission and strong gamma emission that facilitates its identification. 249 Cf is not formed in large quantities in a nuclear reactor because of the slow beta decay of the parent isotope 249 Bk and a large cross-section of interaction with neutrons, but it can be accumulated in the isotopically pure form as the beta decay product of 249 Bk. Californium produced by reactor irradiation of plutonium mostly consists of 250 Cf and 252 Cf, the latter being predominant for large neutron fluences, and its study is hindered by the strong neutron radiation. Among the 16 known isotopes of Einsteinium with mass numbers from 241 to 257, the most affordable is 253S. It is an alpha emitter with a half-life of 20.47 days, a relatively weak gamma emission and small spontaneous fission rate as compared with the isotopes of californium. Prolonged neutron irradiation also produces a long-lived isotope 254S. 19 isotopes of fermium are known with mass numbers of 242 to 260. 254 Fm, 255 Fm and 256 Fm are alpha emitters with a short half-life, which can be isolated in significant amounts. 257 Fm can accumulate upon prolonged and strong irradiation. All these isotopes are characterized by high rates of spontaneous fission. Among the 15 known isotopes of mendelevium, the most studied is 256 Md, which mainly decays through the electron capture with a half-life of 77 minutes. Another alpha emitter, 258 Md, has a half-life of 53 days. Both these isotopes are produced from rare Einsteinium, that therefore limits their availability. Long-lived isotopes of nobelium and isotopes of lawrencium have relatively short half-lives. For nobelium, 11 isotopes are known with mass numbers chapters 250 to 260 and 262. The chemical properties of nobelium and lawrencium were studied with 255 No and 256 Lr. The longest-lived nobelium isotope 259 No has a half-life of 1.5 hours.